Hello everyone, today we will be going over the blind 75 in C++, and today we are working on kth smallest element in a binary search tree. Now, before we get started, feel free to pause the video to take some time to look over the questions over what we need to do to break down the problem. First, we got to figure out what the input is going to be, what data structure / algorithm / technique to use, what to do with the data, and then what our output is going to be. So, to be able to break down the problem, given the root of a binary search tree and an integer k, return the kth smallest value, 1 minus index, of all the values of the nodes in the tree. So, based on the problem, and we can even look at our parameters at the same time, we have tree, node, or root, and then we also have this as well. We have our input of a root of a binary tree and an integer k, where it looks like, just from breaking down the following problem. So the problem is asking us, we need to find the smallest value, 1 minus index, of all the values of the node in the tree, but we have to be at this kth. So what does that mean in particular? Because this question can be a little bit tricky. So if I were to explain this even further, for example, so say for instance we have this binary search tree that we have of, I'll just put it right over here just for safe measure that we have. So we have a root 3, 1, 4, null, and then 2. Then we have k is going to be equal to 1. What it's asking us to do in this case is to take all of the elements which are right here. So we would have, we have this accordingly, and we are going to sort them out first. So we have 1, 2, 3, and 4. And it's asking us the smallest element throughout the rest of our binary search tree that we need. It's just, alright, and our output for this one will be 1 accordingly, because the value that we have at 1, that's the smallest within this area, is 1. Now if we were to go over the second example, if we were to have root for this following binary search tree, and then we have k, what we need to do for this specific problem is that we need to first sort everything out, 4, 5, 6, and then we also have null and null, but really we're just focusing on the following numbers right here, and those will be gone. So what we need to do is that we need to find the third smallest element accordingly, and so our output would be 3. That is what they mean by the kth smallest value at the following indexed. So what we need to do is that we need to find a way where we can, 1, sort all the values within our binary search tree, and then according to k, find the kth smallest value which is indexed at the given position. So if we were to have, for instance, k be 4, for example, the solution would be 4. But our biggest problem that we have is that we have a given binary search tree that's not in order. So I'm going to introduce you folks to a technique that we would use, and I'll just get rid of this for the sake of clarity because we can look at the examples over here to further understand. The technique I'm going to be introducing you folks to is really going to be using a in-order traversal. Where in-order traversal, what it's supposed to do is that it starts from the very leftmost type of element accordingly, then it goes to the root of the following tree, and then heads over to the right accordingly. Because in a binary search tree, the way we divide up each of our numbers accordingly is that typically most of the values that we have are that are less than the root of a given tree are going to be on the left, and the ones that are on the most on the root of the binary tree are going to be on the right side. So we already recognize this behavior that we have, for instance, of 3. Since 2 is less than 3 over here for binary search tree, it's going to be on our left-hand side, and then since 4 is more than 3, it's going to be on our right-hand side. That's just by principle of binary search trees, namely. And so in order traversal, just be able to write out the method for it, is that we're going to find the left node, then we're going to go back to the original node, or the root node, per se, just for the sake of clarity. And we're going to be going through every single subtree accordingly for our technique. Then we finally head over to the right, so we can sort all the numbers accordingly. Because first what we need to do, and I'm just going to put it back on, if we have this, or over here, we got to sort it to 1, 2, 3, 4, 5, 6 to find our output of the third kth smallest element. So it would be 3. We are just trying to replicate this type of behavior accordingly so that we can figure out how to sort our binary tree, because one of the biggest issues that we have is that our given data that we have is not even sorted. So we need to find a way to be able to sort it. And we're told that it's a binary search tree. So we will be following this pattern accordingly. And now, oh yeah, I will write out the output. We need to return the smallest output based on k accordingly. Okay, so now to give a breakdown on the following steps that we need to do is that I'm going to first write this out in 4 steps, so that way we know exactly what to do, and then I'm going to be expanding further on our 4 steps as well. So what we will be doing here is that for our first step, we're going to focus on our edge case for trees, is that we're going to initialize a variable count to 0. And then what we're going to do is that we're going to be creating a function called inOrderTraversal, which will take in the root of our given tree, the k element that we have, as well as our count, which will represent our number of nodes that we have accordingly while we are going through the rest of our tree. And so once we have done that, we're going to go over to step 3 for inside our inOrderTraversal function. And I'm just putting it right here. Okay, what we will do is that at each visited node during the inOrderTraversal, we're going to increment our count by 1 to indicate we have visited. But then next thing we'll do is that we are going to have the edge case where if we have a node be null, we will return the value indicating it's not found. We'll be treating it as return -1, given the fact that we are working with an integer in this case for a function. And then what we will be doing is that we will be doing inOrderTraversal by creating our left node, which will be treated as inOrderTraversal. We're going to do a bit of a recursive call, node, left, k, and then count to keep the parameters accordingly. And then what we will be doing is that if there is no null value for the left node, we will return our left, then we will increment our count. And then what we will be doing accordingly is that if the count becomes equal to k, we will return the value of the current node as the kth smallest element, because we can neglect all the other ones as well, because we only care about our kth most element that we would have. And then finally we would be, what would we do is that we can do a recursive call again, but for the right hand side, where we'll be doing this over here. Let's make this as 4, but it's still technically in there. I just want to be sure on this. Yeah, it's still in there. So I'm just going to make this as 3G, do a recursive call, but you have the right side of in right. So that's how we will do it. And given the fact that we are just returning our following, what we will be doing is that this will be our output. Okay, now just to be able to write up everything else. So for step 1, we're going to first initialize the count, which will indicate the number of nodes we have seen. Then what we will do is that this will be our output. We will return the value from an in-order function, reversal. Yep, so we will have root, k, and then count. Accordingly, now what we will do is going to put this up here for the sake of clarity, keep it all clean. I'm going to create a private function accordingly. So private int in order traversal tree node int k int and count. This is all the fun part, so this is going to be 3. Yep. So you'll have 3A, 3B, 3C, 3D, 3E, 3F, 3G accordingly, just to organize it all together. Remove the white space for clarity. Alright, so for 3A, what we will do is that we're going to focus on our edge case right over here. If the node is null, we're going to return -1 as our edge case that we have. And then for 3B, I apologize for this confusion over here. I'll make this 3A to start with, just for the sake of clarity. I'm also going to put these in the comments as well, just to clarify on this. There we go. That's better. Okay, so for 3B, then we will have int left. It's going to be in order traversal node left k and count. Then okay. If left doesn't equal -1, that means there's a value of this right there. We're going to return left in 3D, we will increase our count accordingly. All right. If the count will be equal to k, we'll return node value right over here. And then what we will do for this part is then return the in order traversal for our node on the right k and count accordingly. Alright, just making sure I have all the steps needed prior to. So we have left, we're going to increment our count. Yes, it's already there. Node val. Okay, it's right there. So again, apologies for the confusion on this. I'm going to put this solution in the comments so that way you can be able to walk through each step accordingly and be able to take this with you to further understand. Let me just run this to be able to make sure that everything is correct. Namely, I'm just going to move all this out. You folks can actually understand and see the whole thing. And then our output. There we go. All right, it passes all the test cases. That's good. And time to submit. Ta-da! Okay, this is great. This is great. And again, the solution will be entirely in the comment section. So to be able to give a breakdown on our time and space complexity for the following. So our time complexity for the solution is going to be O of h plus k, where h is representing the height of the binary search tree and k is our given integer. When we have a worst case scenario where the binary search tree can be skewed, resulting in a height of n minus 1, where n is the number of nodes in the tree. And our space complexity for a following solution that we have is going to be O of h, given the fact that, one, what we are doing is that we are keeping account of everything that is being accounted for every node that we have visited. So therefore, relative to the height of the binary tree, our space complexity is going to be O of h. So yes, this was kth smallest element in the binary search tree. Thanks again for taking time to watch this. If you found this helpful, feel free to like and subscribe. And if you have any other questions, feel free to put them in the comment section. And as always, take care. Cheers. Bye-bye.